Hey guys, today we're going to take a look at 5.6 and we're going to start solving equations that involve either exponential or logarithmic functions. So we're going to start with solving an exponential equation. That's what we're going to do today. We're going to focus on. Okay, now for the most part, to solve an exponential equation, we want to isolate the base. So we want to get the base all by itself. So you'll have a base to a power. Okay, and then we want to rewrite it as a logarithm. So we practiced that the other day. We went from an exponential to a logarithm, and we went from logarithm to exponential. So today, we're going to start with taking this exponential equation, and we're going to rewrite it as a logarithmic equation. So we're going to bring down the x, so x equals, and then our base is 3, so it's going to be log base 3 of 7. That's it. This is now solved for x. The only thing we have to do is we have to figure out what this equals. Well, the other day we learned something called the change of base formula so that we could do this in our calculator. So x equals the log of 7, so the regular common log, or you could even do the natural log of 7, divided by the log of 3. And we're going to put that in our calculator. So let me grab my calculator right here. So it's just log 7, close my parentheses, divided by the log of 3, close my parentheses, and I get 1.77-ish. X equals 1.77, what was it, 1. Okay, and that's it. That's your answer. Okay, look at B. Now B, the first step is isolate the base. Well, that base is not isolated. It's being multiplied by a 5. Now, so we need to get rid of the 5. Well, how do you get rid of something that is multiplying the thing you're trying to get all by itself? You divide by it. So we are going to divide both sides by 5. So 2 to the x equals, well, 3 divided by 5. That's 0.6. So 0.6. And now that we have a base to a power equals a number, we can rewrite it as x equals the log base 2 of 0.6. And again, we can use that change of base formula. Now I'm not going to write it. I'm just going to, in my calculator, I'm going to do the log of 0.6. So the log of 0.6, close my parentheses, and then I'm going to divide it by the log of 2. Log 2. And there's my answer. Negative 0.73, we'll say 7. Okay, we're out 3 decimal places. And that's it. That's your solution. Now, this one, I've got a base to a power equals a number. So this is the situation I want. Okay, my base is isolated. Now it's got a weird looking exponent up here, but that's okay. I'll show you how to handle that in a second. So the first things first, we want to rewrite this as a log. So we're going to write 3x minus 1, because that's our exponent. So the entire exponent comes down. And then we're going to write the other side as the log base 2 of 32. All right. Well, now that we've got this logarithm, let's go ahead and figure out what this equals. So in our calculator, we're going to take the log of 32 divided by the log of 2. I would ask you to do this as well. Don't just trust my calculations. All right, and we got 5 as an answer. So this simplifies down to just the number 5. Okay, well that makes sense because 2 to the 5th power is 32. This is like a perfect power of 2. Now, what do we have now? We have an algebra 1 equation. Okay, we just need to add 1 to both sides. We need to divide both sides by 3. And that's our final answer. X equals 2. That's it. Okay, so try to do D using the example I just did. So pause the video. Try to do D, and then see if you can get the same answer that I do. Alright, so this is what you should have got. So here's me rewriting it as a logarithm. I found the log base 3 of 81 to be 4, and then I just subtracted 1 from both sides, and I got 3 as an answer. Now, these last two, now this method always works. Okay, if you have a base to a power equals a number, this method always works. But I am going to show you another way to do C and D, And this is going to help us with some other types of problems that we could have where we don't just have a base to a power equals a number, we have a situation like this, where we have a base to a power equals a base to a power. Now notice the two bases are identical. That's important. If you are taking two bases to an exponent and the two sides equal each other, well, if the two bases are identical, the only way that your two sides can be equal is if the exponents are also identical. What this says is, if you have a base to a power equals a base to a power, and those two bases are the same, then we also know that the two exponents have to be the same. So we can just ignore this, set the exponents equal to each other, and we'll have this little easier algebra expression. Okay? So, look at my directions, simplify both sides of the equation, rewrite both sides so that they have the same base, and then set the exponents equal and solve. So let me show you. This is example C that we just did. 32 just so happens to be a perfect power of 2. Okay, 32 is 2 to the 5th power. So if I left this side as 2 to the 3x minus 1, and I rewrote this as 2 to the 5th power, since these two bases are identical, the only way the left and the right side can equal each other is if these exponents are identical. So just set the exponents equal to each other, and there you go. We just saved ourselves just this one little step right here, okay, where we had to do it as a logarithm, and then we also had to do like the change of base, and we had to put it in our calculator. But if you know it's a perfect power, you can just set them equal, and then you're done. 3x equals 6, x equals 2, and that's the answer. Now maybe you don't know that 2 to the 5th power is 32. Maybe this one is a little bit better. Okay, 81. You know that 81 is 9 times 9, but since 9 is 3 times 3, then that means that 81 is 3 to the 4th power. But, same base, that means these have to be the same exponents. So, set the exponents equal, and then figure out the x that would make those exponents equal, which in this case is just a 3. Okay, look at C. So I've got 3, I've got a base of 3, and then I have the number 27 over here. Well, the number 27 is 3 to the 3rd power. So if I leave this side as x squared minus 7, and I rewrite this side as 3 to the 3rd power, now, the 27 is being taken to the 2x power, so my 3 to the 3rd is going to be taken to the 2x power as well. All I did was rewrite the number 27. But now, my bases are the same. So if the bases are the same, the exponents have to be the same. So over here, I have an x squared minus 7. Now over here, I had a power to a power. And if you take a power to a power, you multiply them. So the 3 and the 2x just multiply together, and I can just write that as 6x. And now I have a quadratic equation when you solve now. So this is a more complicated algebra problem, but it's just an algebra problem. We took this exponential problem and turned it into just an algebra problem. X squared minus 6x minus 7 equals 0, because I want to get I need to get everything on the same side. And then I can, this will factors of negative 7 that add up to negative 6 would be minus 7 and plus 1. And so I would get x equals positive 7 and negative 1. So this one has two x's that'll work. And if you plugged either one of those into the original problem, you would get the two sides of the equation would equal each other. Okay, so again, if you can write the bases the same, or if the bases are already the same, then you can just ignore them and set the exponents equal. So like, look at this next one. This next one looks crazy. Okay, I've got e to a power, so here's a base to a power, and then over here I have e to a power times e to a power. So the first thing we need to do is we need to simplify this right-hand side. So 2x minus 1 equals, now I have two bases that are multiplying each other. When bases multiply, their exponents add together. So I've got this minus 3x and I got this minus 4x. Those are like terms, so they can actually add together, and you can get minus 7x. But now I've got that situation where I've got the same bases, So all I have to do is set the exponents equal. So 2x minus 1 equals negative 7x. And now I just have an algebra problem to solve. I would get my x's on the same side, so I would like subtract the 2x from over here, which will give me negative 9x. Now I'm going to divide by negative 9. I'm just going to leave, so negative 1 divided by negative 9 is going to be positive 1 over positive 9, and I'm just going to leave my answer like that. Okay, that's if you put it in your calculator and got a decimal, that's fine, but that seems like a pretty simple way to write that. Okay, just 1 over 9. All right, one more. So look at E, or example E. So again, the left side is good. I've got a base to a power. The right side, I've got a base to a power times a base to a power. Now it's the same base, so we're going to rewrite it by adding the exponents. Now, be careful. These exponents are not like terms. Okay, this is a negative 3 and this is a 2x. So when I combine them together, they're really not going to combine. They're just going to be written as negative 3 plus 2x. That's all I can do. I can take the two exponents and I can add them together. Okay, but now I have a base to a power equals a base to a power. Ignore the bases, set the exponents equal to each other. Negative x squared equals negative 3 plus 2x. And then let's solve. This is a quadratic equation to solve. Whenever you solve a quadratic, you always want the x squared to be positive. So I'm just going to move this minus x squared to the right. 0 equals, that'll be x squared. Then I'm going to put the 2x. Then I'm going to put the minus 3. And now this is a quadratic that can be factored. Factors of negative 3 that add up to 2 are going to be plus 3, and then a minus 1. That's where the negative 3 comes from. We have a positive and a negative. But then this means that x would equal negative 3 or positive 1, which means we have two solutions to this one. Okay? All right, so now that we know how to solve some exponential equations, I want to recall some of the word problems and the formulas we looked at earlier, and to show how we could solve these for the exponents, which we haven't done yet. Okay, so when we looked at the compound interest or the continuous compounding formula, we were always given a certain amount of money, or maybe trying to figure out how much money we would start with to end up with a certain amount. But these, now we're going to be able to do things a little differently. So if you look at this example, how long will it take? So we're trying to figure out an amount of time. Well, time is our exponent up here, or up here, okay, depending on the problem. So we're going to be solving for one of our exponents. So how long will it take an initial investment of $10,000 to grow, so this is our initial amount, to grow to $25,000, so now that's our future amount, with a rate of 6% compounded continuously. So we're going to be using this formula. So 25,000 equals 10,000, and then e to the 0.06 t. All right, so the rules from the previous page said if we've got a base to a power, we need to isolate the base. So right now it's being multiplied by a 10,000. So we need to divide both sides by 10,000. So 25,000 times 10,000, well, 25 times, or divided by 10 is going to be 2.5, and then e to the 0.06 t. Now, I've got a base to a power equals a value. So I can rewrite this as a logarithm. This is a base e, so this is going to be a natural log. So 0.06t is equal to the natural log of 2.5. Once we've got this is now a calculator problem. We're just going to take the natural log of 2.5. So let me clear this out. Natural log 2.5 equals, okay, and then we're going to divide that by the 0.06 that's multiplying our t to get the t by itself. So we're going to divide by 0.06, and I get 15. We'll say 3. So 15.3 equals t. So the problem was, how long will it take an investment of 10,000 to turn into 25,000? Well, it's going to take over 15 years for that to happen. That money would just have to sit there. Okay? Look at the next one. 1,000 is invested at 8% compounded monthly. How long before you have 1,500? So we're going to end up, now I did not give a lot of space here. I'm going to start over here. I may have to do kind of two columns. So 1,500 equals, we're starting with 1,000. Now, this is compounded monthly, so this will be this formula. So 1 plus 0.08 divided by monthly is 12 to the 12t power. Okay? So we need to simplify this. I'm going to do two things. First off, we've got a base to a power. I don't really know what that base is, so we need to simplify that and figure out exactly what's going on in these parentheses. But we also need to get the base by itself. So I'm going to divide by this 1,000. So I'm going to divide by 1,000. So that's going to be 1.5 equals. Let's figure out what our base is. So clear. So 1 plus 0.08 divided by 12 is 1.00. I know I'm writing down a lot of things right here. Looks looks like it's 6 repeating to the 12t power. All right. So to solve this, this is now a base to a power equals a value. I need to write this as a logarithm. The base of my logarithm will be the base of this exponential over here. So it's going to be the log base 1.006 repeating, that's my base, of 1.5 equals 12t. All right, so this, yes, I get it. That is a very, very odd base, but we've got the change of base formula that will do this for us. So I'm going to come over here now. 12t is equal to the log of 1.5. So log of 1.5, and then divided by the log of 1.00, and then it was just a bunch of 6s. So I'm going to get 61 point, what was that? 0.223. And then we're going to divide by 12. So divide by 12. And I get 5 let's call that 5.09. So t is 5.09. So it'll take you about 5 years to turn $1,000 into $1,500 at that interest rate. Okay, so those are some money problems. Let's take a look at the growth and decay problems that we looked at earlier. So this is the same problem we had earlier. We have a colony of bacteria growing at a certain rate. Okay, how long will it take for the population to reach 140 grams? So this is our initial amount, 90. We want to know how long before our future amount is 140. So 140 equals 90 e to the 0.05 t. So just like what we did with the money, we're going to divide by 90. So 140 divided by 90. So what looks like 1.5 repeating equals e to the 0.05 t. This is an e, a natural number, so we're going to take the natural log of the other side. So the natural log of 1.5 repeating equals 0.05 t. So I've got two steps. I'm going to do the natural log of this, which is in my calculator. So I can do the natural log, and then I can hit the answer button. And then we're going to divide by the 0.05, and that's our answer. So t equals 8.8. I think this is in days. So it'll take 8.8 days to go from 90 to 140. Okay? B says, what is the doubling time? Well, for doubling, if we have 90, it just means when are we going to have 180? So everything else is the same setup. Now, first thing I have to do is isolate my base. So I'm going to divide. Well, 180 divided by 90 is 2. That's not a coincidence. This is a doubling time, so this is what should happen. So 2 equals e to the 0.05t. So we are going to take the natural log of 2. And then we're going to divide that by 0.05. So calculator, natural log of 2, parentheses, don't forget the parentheses there, divided by 0.05, and 13.9, we'll say. T equals 13.9 days. That's how long it'll take to double. Okay? Now, we've got one more problem. This one's a little tougher. Okay? It has to do with half-life. So the half-life, so we've got some radioactive material. The half-life of radium is 1,690 years. So this is T. This is the amount of time that it takes this stuff to shrink down to half its original amount. If 10 grams are present now, how much will be present in 50 years? Well, we've got a problem here. We know what the half-life is, but we don't know actually what the decay rate. We need K. We don't know how fast this stuff is like shrinking. We just know that it takes 1,690 years to go from its original amount down to half. So this is actually a two-part problem. It just doesn't look like it. Okay, you see one question mark, you're being asked one question, you don't realize it's a two-parter. The first thing we have to do is figure out the decay rate. So the half-life is 1,690 years. So using this formula, the amount that I start with, okay, that's what this is. I'm going to start with a certain amount. I am going to end up with half of that amount. That's what a half-life would be. Whatever I start with, I'm going to have half of that over a certain amount of time. E to the, and then I've got a K and a T. Well, the K is what I'm trying to solve for. I'm trying to figure out what that K is. How fast or how slow is this stuff decaying? And the amount of time that it takes to get half of our amount is 1,690. Now, I need to solve this. First thing we're going to do is we're going to notice that these two A's are going to cancel each other out. I've got an A on this side and an A on this side. If I divide both sides by A, they're going to cancel, and I'm going to have 1/2 E, and then I'm going to flip these around so it looks more normal to us, where we have the number first followed by the variable. That's it. Okay, I just need to do this, and this is now a calculator problem. Take the natural log of 1/2, divide it by 1,690, and that'll be our K value. So, natural log of 1/2 equals, and then divide it by 1,690, and I get negative 0.000. All right, I'm gonna put 41. Okay, after that there was another 0, so I'm kind of running out of like significant digits. Okay, you could write all those down if you wanted. Okay, but I'm going to write that down. So now we know our K, we know our decay rate. So now this problem over here is pretty easy. Okay, we've got 10 grams present now, so how much will be present in 50 years? So we want to know the amount that we're going to have in 50 years. This is function notation. This isn't something I'm going to solve and divide by 50 or anything. This is just a function notation. Over here, it's going to be my initial amount, which is 10, my E to the negative 0.00041 power times my time, and in this case it's a 50. So I just need to plug all that in my calculator, and that's my answer. The amount that I will have in 50 years is 10 E to the negative 0.00041 times 50, 9.797, we'll say 9.8. Okay, this stuff does not decay very fast. Okay, it takes 1,690 years to go from 10 grams to 5 grams, because that'd be a half amount. Okay, so in a mere 50 years, this stuff is not going to shrink down very much, so 9.8. So that's it. So take a look at your worksheet and let me know if you have any questions on solving the equations or on these word problems. All right, thanks.